Sound can be described as vibrations that travel through the air or another medium and can be heard when they reach a person's or animal's ear. Everything that makes or receives sound has to vibrate. The vibrating particles of sound waves knocks into other particles, which causes them to vibrate and knock into other particles, and so on. These vibrating particles causes our eardrums to vibrate, which sends nerve signals to our brain containing information. Sound can only travel through things that contain particles for it to vibrate too. In our everyday life, the most common obstacle sound travels through is air. Sound also commonly travels through mediums such as air, gas, or metal. Sound cannot travel through space as it is a vacuum with no particles for it to knock into, meaning that there are no sounds in space. An experiment that proves this would be the one done by scientist Robert Boyle. He placed a ringing alarm clock in a glass jar, and while the alarm is still ringing, he sucked all the air out with a pump. As the air gradually disappeared, the sound died out because there was nothing left in the jar for it to travel through. The speed of sound can be simply explained as the speed the waves move. It also depends on the material it is traveling through. The speed of sound in air at 20 degrees Celsius is 343 miles per hour. To calculate the speed of sound while traveling through gas, add 0.60 for each Celsius degree change. Sound can also accelerate so fast to the point where it breaks through the high-intensity sound waves. This is why we often see a jet plane whizzing by before we hear the loud boom of its engine, or why we often see lightning before we hear thunder. The two main features that affects the way we perceive sound is the amplitude and the frequency. Amplitude is the maximum extent of a vibration or oscillation measured from the position of equilibrium. A higher amplitude makes a louder sound. Frequency is the rate at which a vibration occurs that constitutes a wave, either in a material as in sound waves or in an electromagnetic field as in radio waves and light. The frequency of the sound wave tells you about the sound's pitch. A sound with a higher frequency has a higher pitch. Sound intensity is the power carried by sound waves per unit. Power is the rate at which energy is transferred by the wave. In equation form, intensity is equals to power multiplied by the area. Decibel is a unit used to measure a sound's pressure or forcefulness. For example, general city traffic is described as having a sound decibel of 70, and normal conversation have a decibel of 60. Types of sound waves. Longitudinal sound waves. A longitudinal wave is a wave in which the motion of the medium's particle is parallel to the direction of the energy transport. Mechanical sound waves. As sound waves travel through air by displacing air particles in a chain reaction. As one particle is displaced from its equilibrium position, it pushes or pulls on neighboring molecules, causing them to be displaced from their equilibrium. As particles continue to displace one another with mechanical vibrations, the disturbance is transported throughout the medium. These particles-to-particles mechanical vibrations of sound conductance qualify sound waves as a mechanical energy or energy associated with the vibrations created by a vibrating source requires a medium to travel, which makes sound energy a mechanical wave. Pressure sound waves. Because sound waves consist of compressions and refractions, the region fluctuates between low and high patterns. Transverse waves. Transverse waves move with oscillations that are perpendicular to the direction of the wave. Sound waves are not transverse waves because their oscillations are parallel to the direction of the energy transport. Examples of this would be the ripples of a water surface or the vibrations in a guitar string.